One thing that many students find very confusing is this whole idea of how energy is going to flow in these cases. Now, that doesn't seem like it'd be that tricky, but try to decide what a system and the surroundings are going to be in a couple of examples, and you'll quickly start to see why we have to be really, really picky with how we describe our system and our surroundings in order for us to actually understand how energy moved around in a reaction or just in a physical system. Let me explain. So our system is going to be everything that is relevant within a change. We're used to thinking that as being an entire area of space. But it's not always that straightforward, and we'll see some examples of that. Now the surroundings are going to be everything else. Do I really mean everything? Why, yes, I do actually mean going out to a radius of infinity from that is part of the surroundings. Now, realistically, if I'm doing a reaction in my lab setting, I'm not worrying about having heat energy start warming up some portion of Pluto, or one of the exoplanets, or a star in another galaxy. However, all of those are part of our surroundings. That said, we can definitely restrict things in a little bit more than that. Now, it might seem ridiculous to say the rest of the galaxy and universe is part of this calculation, and it is. But let me turn it back on you then. How close in can you get for whatever system you're looking at to decide where the surroundings stop existing for your problem? Now it's a little bit more tricky of a problem. Suppose that what you were doing was you were dropping a hot piece of metal into some water, and you were seeing how much heat energy is going to be transferred. System would be my chunk of metal. Surroundings would be the water and the cup. And we know heat is lost from inside the water in the cup to the air around it. You know that because you know heat gets transferred out because you've probably been outdoors on a cold day holding a cup of coffee or hot chocolate and felt the hot water warm up the wall of the cup and then warm up your hands. And you probably also felt the heat around that. So notice, even in a chemical scale system, we're going to start having bigger and bigger surroundings depending on how we set things up. What we need to do is find a way to limit how far out that goes. And we'll see in other videos that typically what we'll do is we're going to make some sort of a barrier where the heat doesn't quickly cross it going to the outside world. Styrofoam and other insulators like that. Now, let's go for an example here just to show some of what we're talking about. Suppose that we've got this scenario. We're going to mix cold milk, hot coffee, and a room temperature glass and some room temperature sugar. When we mix, what is going to be our final temperature? Well, we know from everyday experience that the coffee is substantially more hot than the room temperature air and the room temperature sugar and the room temperature cup. We also know that the cold milk is going to cool it down some, but because there's so much more volume and so much more heat energy inside of the hot coffee, it's going to be warm once we start mixing it. However, the whole system is going to end up being cooler than the hot coffee was originally. So what we've just done there, I've just described coffee, sugar, milk, and cup as being part of our system. But maybe what we care most about isn't where all the temperature went. Maybe what we care most about is the total final temperature of what I'm about to drink, at which point the cup would not be part of my system. The cup would be part of the surroundings. This is exactly where that cutoff starts to get very picky and very tricky. So make sure that when you do any of these problems, you carefully pay attention to the wording so that you can do a good evaluation of where the wall between system and surroundings will be, and also how much of the universe you're going to chop off from what's in your surroundings.